and general relativity in a single theory that could describe the universe on all scales.
Now, in spite of this, we've made tremendous progress in understanding the universe. But there's a catch. There are strange realms of the cosmos that will never be fully understood until we find a unified theory. And nowhere is this more evident than in the depths of a black hole. A German astronomer named Karl Schwarzschild first proposed what we now call black holes in 1916. While stationed on the front lines in World War I, he solved the equations of Einstein's general relativity in a new and puzzling way. Between calculations of artillery trajectories, Schwarzschild figured out that an enormous amount of mass, like that of a very dense star, concentrated in a small area, would warp the fabric of space-time so severely that nothing, not even light, could escape its gravitational pull. For decades, physicists were skeptical that Schwarzschild's calculations were anything more than theory. But today, satellite telescopes probing deep into space are discovering regions with enormous gravitational pull that most scientists believe are black holes. Schwarzschild's theory now seems to be reality. So, here's the question. If you're trying to figure out what happens in the depths of a black hole, where an entire star is crushed to a tiny speck, do you use general relativity because the star is incredibly heavy, or quantum mechanics because it's incredibly tiny? Well, that's the problem. Since the center of a black hole is both tiny and heavy, you can't avoid using both theories at the same time. And when we try to put the two theories together in the realm of black holes, they conflict, it breaks down, they give nonsensical predictions, and the universe is not nonsensical, it's got to make sense.
Quantum mechanics works really well for small things, and general relativity works really well for stars and galaxies. But the atoms, the small things, and the galaxies, they're part of the same universe. So there has to be some description that applies to everything. So we can't have one description for atoms and one for stars.
Now, with string theory, we think we may have found a way to unite our theory of the large and our theory of the small and make sense of the universe at all scales and all places. Instead of a multitude of tiny particles, string theory proclaims that everything in the universe, all forces and all matter, is made of one single ingredient, tiny, vibrating strands of energy known as strings.
A string can wiggle in many different ways, whereas of course a point can't. And the different ways in which the string wiggles represent the different kinds of elementary particles.
It's like a violin string, and it can vibrate, just like violin strings can vibrate. Each note, if you like, describes a different particle.
So it has incredible unification power. It unifies our understanding of all these different kinds of particles.
So unity of the different forces and particles is achieved because they all come from different kinds of vibrations of the same basic string.
It's a simple idea with far-reaching consequences.
What string theory does is it holds out the promise that, look, we can really understand questions that you might not even have thought were scientific questions. Questions about how the universe began, why the universe is the way it is at the most fundamental level. The idea that a scientific theory that we already have in our hands could answer the most basic questions is extremely seductive.
But this seductive new theory is also controversial. Strings, if they exist, are so small there's little hope of ever seeing one.
String theory and string theorists do have a real problem. How do you actually test string theory? If you can't test it in the way that we test normal theories, it's not science, it's philosophy. And that's a real problem.
If string theory fails to provide a testable prediction, then nobody should believe it. On the other hand, there's a kind of elegance to these things. And given the history of how theoretical physics has evolved thus far, it is totally conceivable that some, if not all, of these ideas will turn out to be correct.
I think 100 years from now, this particular period when most of the brightest young theoretical physicists worked on string theory will be remembered as a heroic age when theorists tried and succeeded to develop a unified theory of all the phenomena of nature. On the other hand, it may be remembered as a tragic failure. My guess is that it'll be something like the former rather than the latter. But ask me 100 years from now, then I can tell you.
Our understanding of the universe has come an enormously long way during the last 3 centuries. Just consider this. Isaac Newton, who's perhaps the greatest scientist of all time, once said, "I have been like a boy, playing on the seashore, diverting myself in now and then finding a smoother pebble or prettier shell than usual, while the great ocean of truth lay before me, all undiscovered." And yet, 250 years later, Albert Einstein, who was Newton's true successor, was able to seriously suggest that this vast ocean, all the laws of nature, might be reduced to a few fundamental ideas expressed by a handful of mathematical symbols.
And today, a half-century after Einstein's death, we may at last be on the verge of fulfilling his dream of unification with string theory. But where did this daring and strange new theory come from? How does string theory achieve the ultimate unification of the laws of the large and the laws of the small? And how will we know if it's right or wrong?
No experiment can ever check up what's going on at the distances that are being studied. The theory is permanently safe. Is that a theory of physics or a philosophy?
It isn't written in the stars that we're going to succeed, but in the end, we hope we will have a single theory that governs everything.